Okay, good morning. So, let's see. I hope everybody's doing well. Welcome to Monday morning session. Uh, Today we're going to be moving on to another chapter, chapter 9, starting on chapter 9. And um, yeah, I hope you all are doing well and holding up as we kind of get to the last uh, last lap or two of class. I had been thinking about some different aspects of how things were going to come together, and I tried to summarize that in an email that I sent everybody yesterday. So look that, read that over carefully, please. And if you have any questions or concerns or anything as we get towards the last week, let me know. So there's also a survey on Blackboard that is designed to give me a chance to get some information from you about the final. One of the things I've been thinking a lot about, and I just want to have our ducks in a row before the last week, is the final, making sure that we have everything straightened out in terms of how we're going to actually do that. Because I think uh, what I don't want you to be in a position where you have to worry about one final, bumping into another and stuff like that. That just seems like a mess. So I want to be logical about it, and that's an effort to try and get some information from you. Um, and I'll be following up as well with things like missing lab reports and other issues. Part of the delay in that is it's just taking me a long time to grade them on the computer, but I want to get that all uh, wrapped up so you know exactly where you stand as we get into as we get into the end of the quarter. So, um, yeah, we can take a couple minutes. Does anybody have any questions about any of that? I mean, also, if you have questions that you don't want to talk about in this space, shoot send me an email, contact me on Teams. We can get things straightened out. Um, cool. Okay. Well, like I said, if you have other questions, ping me on Teams or on email, and we'll get them straightened out. Otherwise, let's jump into momentum conservation. Momentum. This is uh, this is perhaps a more fundamental idea than energy conservation. I think in part it gets a little less attention, or you're maybe less familiar with it because it's a little bit more difficult to explain. Um, but energy conservation, it seemed like most students had, if you had taken physics before, you'd been exposed to that idea, and it's pretty intuitive. The amount of energy has to stay the same. It can't destroy energy, etc. Have you guys dealt with momentum or momentum conservation before? Have you learned about this? Yeah, objects hitting each other. We talk about it in the context of collisions. So maybe some have. Um, yeah, so we'll get into collisions, not so much today, but more tomorrow. But that's kind of the classic example. A lot of times, uh, sort of the quintessential problem will be billiard balls or something where they collide, and you may have memories of solving problems involving figuring out like the speed of a ball after a collision or the angle or something like that. And that's kind of where we're headed, but we need to introduce some fundamentals first. So what we're going to be talking about is basically the first three sections. Yeah, okay, so if you've heard the terminology elastic and inelastic collisions, then you have run into this stuff before. So this is, we'll start with the first three sections of Chapter 9. And we're going to look at tentatively these example problems, which are just the problems from the back of the from the the end of the chapter 10, 11, 23, and 26. And we'll see how much time we have because I want to be better about ending before or ending on time. So basically, the context where we're coming from is we've been talking about energy conservation. And that was in chapter 8. And that was built on top of work. That was built on top of Newton's laws. And now what we're getting into is momentum. So the first thing we need to know is what is momentum exactly? So like many things that we talk about in physics, force, inertia, work, momentum is one where we probably have some sort of colloquial notion of what it means. You might say, oh, we have a lot of momentum going into doing something or something, and you have this sense of it keeps like a inclination to keep doing something. Well, the definition for momentum in physics, at least the linear momentum, is we use the letter P to denote it, and it's an object's mass times its velocity. So if you have, some object of mass m and it's moving at some velocity, it has a momentum given by its mass times its velocity. And the unit, for momentum is nothing, there's no special unit for it. It's just the units of mass times velocity, so kilograms meters per second. And let's see. I wanted to say that where we're going with this is momentum conservation, i.e., we'll flesh this out more as we go in the chapter, but let me put it this way. So we're headed toward momentum conservation. And like I mentioned at the top, this is perhaps a more fundamental idea than energy conservation in some regards because there are lots of circumstances where energy is not conserved, so to speak, but momentum is. So, in other words, there's situations where you will conserve momentum, or momentum will always be conserved, but energy is not necessarily conserved. And we talked about some of those distinctions in the last chapter, the difference between mechanical energy and total energy conservation, and how you could have energy that's lost to heat and non-conservative, the work done by non-conservative forces. And then what it'll mean in this context is just like it was mentioned, elastic and inelastic collisions. So some collisions you'll conserve energy and some you won't, in other words, but you'll always conserve momentum. So that's kind of where we're headed to foreshadow that a little bit. So part of why I think momentum is kind of interesting is that it really speaks to how calculus is kind of the language to talk about physics. So let me give you a couple pieces of information, flesh this out a little bit. Um, put it to you this way. So I suspect you've seen, momentum is mv. Oh, and notice, of course, this is a vector. Momentum is a vector. So when we get into more complicated problems of momentum conservation and collisions, much of what makes this material challenging is because you have to keep track of the directions of things because momentum is a vector. So when you start conserving momentum in 2 or 3 dimensions, things can get fairly complicated because you have multiple vector components, multiple objects, and you have to keep track of their directions and their speeds. So, but anyway, so momentum is, like I said, an excellent example of how calculus is the natural language of physics. And what I mean is check this out. So you can write, you can rewrite Newton's second law like this. Okay. So before we had introduced, not happy with my sigma here. We had introduced Newton's second law as the sum of forces on an object is equal to that object's mass times its acceleration. Well, it turns out that when Newton originally formulated this, he didn't state it that way. He stated it instead as, in modern language terms, as the derivative of momentum with respect to time. And if we put in what the definition of momentum is, mass times velocity, now, if you have a product, right, you can do product rule. Generally, the mass is going to be constant. So this would just be m dv dt, i.e. m times acceleration. So we get back recover our familiar expression for Newton's second law, but this is a more general starting point. And we didn't state it this way originally because this would have required us to use a derivative, right? And when we were just introducing these topics, we were less, we kind of talked about calculus less. But this, like I said, is another example of how calculus is really, the natural language to discuss a lot of these ideas. And to the point that this is a more general formulation, consider the situation where, so consider this. If mass is not constant, you can also have, so how would you do this? If mass was dependent on time as well, you'd have a product of two things that change with time. And so you would end up with dm dt times v, or let me put it this way. Derivative of the first one times the second plus these. Now, the first term would be 0 if the mass was constant, but if it's not, you have two contributions. And this term that looks like dm dt, this contribution because of a change in mass with respect to time, this is what you need to explain things like rocket propulsion. So not only is this a more powerful way, or a more general way of describing Newton's second law. There are some kinds of problems that you just can't explain unless you consider the fact that the object's mass is changing. And the rocket propulsion, there's a section in the book. Hopefully, we'll be able to talk a little bit more about it. But there was some controversy when people were proposing, around the time when rockets were first being invented, about how could you have a rocket accelerate in outer space when it's not pushing against anything, right? So we were we've described forces, pairs of forces where you have an object. If one pulls on the other, then the other one pulls back. If one pushes on the other one pushes back, etc. Well, if you're in the vacuum of space and you're pushing stuff out, but it's not pushing against anything, how do you get an acceleration? Well, it turns out that if you just look at it in a little more detail and consider the fact that there's the mass is changing, you can easily describe it in terms of Newton's second law and in terms of an acceleration. So I think this is kind of an interesting, not to beat this to death, but just the power of calculus to explain things in a little more detail. Okay, so any questions so far? Yeah, that's a good question. Huh. Oh, sorry. This word is propulsion, or it's supposed to be. Rocket propulsion. Um, yeah, to your question, Caleb, mass increasing over time. Um, maybe there's less to talk about in that regard. They talk about there's some problems. Actually, we'll look at an example problem where you add mass to an object and you have to conserve momentum. But I can't think of anything off the top of my head where you have an object that's like sucking stuff up and increasing mass. But I'm sure there are some situations. I just can't think of anything. But yeah, that's an interesting, what would be the complementary situation? I'll have to think about that. So the next idea, yeah, I suppose, or maybe something like sucks up water and collects and gets more massive. I'm sure there's some interesting situations. Uh, so we now know what momentum is. We've connected it back to what we were doing way back in what is it, chapter 4 with Newton's laws. And the next idea that we want to consider is conservation of momentum. And it sounds like folks are at least somewhat familiar with this. And let me state it for you. So when no net external force acts on a system, the total momentum of the system is conserved. So this is introduced in section 9.2. And so, of course, read that. But kind of the cartoon that they would present in this picture is, you have objects that have some mass and velocity, and, they whack into each other. There's some kind of, like I was mentioning, the prototypical example is you have some kind of a collision, like imagining pool balls or something. And, they're going to collide, and usually one way to denote before and after in terms of velocity is you add a little prime, a little sort of apostrophe to the variable, and that tells you that you're distinguishing the velocity before from the velocity after. So, and I'm just drawing you a cartoon. Like, this doesn't have any, I'm not actually quantitatively describing the size or angle of these vectors, but it's just to give you a sense that before and after they're going to have to remain the same. So we can write this mathematically as the momentum before, i.e. MAVA plus MBVB, is going to have to equal the momentum after. And another way to put this, which is nice and concise, is that the total momentum of an isolated system remains constant. So, and I'll draw your attention to this word isolated. So this picture that I've drawn you, you can think of this as sort of, or when we use the word like, when we talk about something as being a system or an isolated system, etc., really think of this as being sort of apart from anything else. So I can symbolize that by drawing a box around it and saying, hey, this is separate. So, and why this matters is because this is not going to hold if you have some external force that's acting on everything, okay? So if if we had, well, really the only force at a distance that we've talked about is gravity, but if you can imagine, if there's gravity, you could have things accelerated by gravity, and in that case, you would have, an external force, and so the momentum, perhaps in one direction anyway, would be changing, and so this picture that wouldn't hold in that circumstance. So we have to think of this as being a system apart from everything else. And like I had mentioned, kind of foreshadowing, going forward, doing this, the math behind it. So let me put it this way. Foreshadowing. Conserving moment. So conservation in 3D is much of the sort of the meat of this topic, this chapter. Because you'll have situations where you need to just write equations in x and y for each mass before and after, and so it amounts to, the idea is pretty easy to state, but it can result in a fair amount of algebra because you have a lot of masses and velocities and components of velocities to keep track of. Anyway, so that's kind of where we're going to be headed in sort of the latter sections, like 9.4 and on going forward. So that's the idea, though, conservation of momentum. And we'll practice this today with some simple problems, basically like in one dimension. But before we do that, I want to introduce one other idea that's sort of another calculus connection, which is kind of cool. And that is, so I'm just going to keep on because it sounded like you guys were pretty familiar with momentum conservation. So we'll practice it. So you can kind of, keep your questions on that until we look at some example problems. But I want to introduce one other idea, and that's impulse. So, and this is another calculus connection. And it's really interesting and useful. Let me actually. It's really useful when talking about impacts, collisions. So recall, we had just introduced Newton's second law this way, that the force is dp dt, or that we can define the force as the derivative of momentum. Well, if we reorganize this, we could, write it as the force times dt, our differential time slice, is going to equal a differential of momentum. And then the natural thing to do with this is to integrate it. So if we integrate this, the integral of this differential momentum is going to be the change in momentum. So which we can think of as P final minus P initial. And that is equal to this thing, this integral of force, over the same limits. And this quantity, this thing, is called the impulse. And your book uses the letter J to denote it. A capital J. I feel like that's not very illuminating as to why it would be called that, so I'll usually just call it impulse. But now, why this is useful? So generally, it's pretty difficult to know the functional form of a force when you're whacking things together, because it looks, if you imagine, if you crack like crack some objects together, there's going to be a large force. So the force as a function of time would not be an easily described function, because it's just like, it's a sharp peak or something. But what you can do is you can say, okay, we can specify like an average force over some delta time. So if you know the duration, in other words, if you know the duration of an impact and you know the change in momentum, you can specify what the force average will be. And I'll show you an example where they have a better picture than this, but you can kind of see what I mean. So if you imagine, we're talking about like the area under a curve, right? If we were to integrate over this weird force function, if instead we just specify the average, the area of those two objects would be the same. And so it allows us to give sort of an estimate of the force in an impact. And that's the part that's useful. So in other words, if you know the duration, or you have an estimate of the duration, you can find the average force. So this is a definition, and we'll make use of this in a second with an example problem. But I'm curious, have you ever encountered this terminology before, impulse? Ah, okay. Oh, okay. You've already seen it? Ah, okay. Well, that's good. Then that'll be. I think it's a little more. You've been called impulsive, funny. Okay, so I think, like I had mentioned with regards to Newton's second law, expressing it in terms of the derivative of momentum, this is another example of just how, of kind of the explanatory power of calculus as the language of physics. There's just really, uh, so yeah, if we haven't talked about calculus as much, then this idea becomes a lot more difficult um, to explain. So anyway, let's look at an example or see what examples we can get through. So examples. So these are in your textbook. Um, let's see here. No, this is not the example that I want. Sorry, one moment. Ah, okay. So consider this question. Make this a little bigger. A 9,000 kilogram railroad car travels on a level frictionless track with a constant speed of 15 meters per second, and then a load is dropped into it onto the car. What will be the car's new speed? So this kind of speaks to your question before, or the comment before about what about a situation where the mass is changing. Now we don't need an integral to do this because it's just discretely changing by some amount, but it's a situation where mass is increasing. So let's try and draw a cartoon of this. We have a railroad car that's moving at 15 meters per second. This thing has a mass of 9,000 kilograms. And let's call this before. And then we're going to, imagine goes to a silo or something and gets filled up. If I can draw. So, now there's a load in the car. And, we want to know what the velocity after is going to be. So this is one of the more simple problems that we can approach in terms of momentum conservation, in part because it's a one-dimensional problem. So it's sort of there's less things that we have to worry about. So in other words, if we state momentum conservation, for us, the initial momentum is going to have to equal the final momentum, and we're constrained to one dimension. So this will be pretty straightforward. It's just the mass times the velocity initial is going to have to equal the mass times the velocity final. Now the mass has changed because we're going from mass plus the mass of the load times the velocity, call it velocity b. And so if we want to know, actually, I'll try and use the same terminology because you're going to see this when we're talking about collisions, VA and VB. So let me put it like this. The velocity of A plus B. So this is just for consistency with the stuff that we'll encounter later. We can then solve this for V. And we can put in our numbers here. So this car was 9,150 kilograms times 15 meters per second divided by 9,150 plus 4,350. This would be about 10 meters per second. And this is what I've called VA plus B. So it started at 15 meters per second. It's going to decrease to 10 meters per second so as to conserve momentum. This is a sort of, very simple example of momentum conservation in one dimension. Questions? So that's kind of the simple, a really simple example, but it gives you a sense of, the different quantities that you're working with, etc. So. And just to clarify, this should be question 10 out of the book. So if you want to see this written in the book, you can look at it there. I suspect if you've dealt with this before, with momentum conservation before, you're like, okay, cool. Let's look at a couple other problems. So let me paste another one in here. What? Okay, here, check out this problem. So we have an atomic nucleus at rest decays radioactively into an alpha particle and a smaller nucleus. What will be the speed of this recoiling nucleus if the speed of the alpha particle is 2.8 times 10 to the 5 meters per second? And assume the recoiling nucleus has a mass 57 times greater than that of the alpha particle. So one thing that's so this is this is actually a pretty simple problem, but I would point out that these ideas of momentum conservation and energy conservation and stuff, a lot of times, Caleb had mentioned inelastic and elastic collisions. Really, in reality, one of the few circumstances where you can have actually elastic collisions is when you're talking about nuclear physics. So these kinds of problems are interesting in that it's giving us just a little taste of that. So let's consider this one. So this nucleus is at rest. So what that means is, in terms of momentum, is that this is another way of saying that the initial momentum is going to equal 0. I can draw a 0. So what that looks like is we have, imagine like you've seen cartoons of an atomic nucleus. It's made up of protons and neutrons. And this thing is going to break apart. We're going to have a radioactive decay where most of the nucleus is going to go in one direction. And we don't know what that velocity is. But we're given that an alpha particle. So do you guys know what an alpha particle is? So we're given that an alpha particle is going to break off, and it's going to have a velocity of 2.8 times 10 to the 5 meters per second. So an alpha particle is like a helium nucleus. It's a kind of radioactive product. There's alpha radiation, beta, gamma radiation. These are different products, but it's basically a helium nucleus. So you can have a kind of radioactive decay where you have a nucleus spit out essentially a helium nucleus. So in this example, that's what's happening. We spit out a helium nucleus at some velocity, and we want to know what the velocity on the other remaining chunk is. And we also know that that remaining chunk has a mass that's 57 times larger. So in other words, the majority of it is with the remaining chunk. So let's look at this in terms of momentum conservation. So the momentum initial is going to have to equal the momentum final. We started with 0. So the momentum final we can write as the mass of the alpha particle times its velocity plus the mass of 57 alpha particles. Or let me put it this way. 57 mass alpha particles times this velocity that we don't know. Put a little question mark there. So we can then solve this for that velocity. What is this velocity? Well, we would subtract, let me rewrite this, we would subtract this over, and then we would divide. Notice that, well, since the problem, we don't have to actually know what the mass is because it's common. They gave it to us in terms of a multiple. So the mass is canceling out because it's a really small number because we're talking about atomic particles, right? So we then have this negative V alpha divided by 57. We put in the number negative 10 to the 5 divided by 57. Crunch the numbers, we get negative 4.9 times 10 to the 3 meters per second. So this is our velocity question mark that we've specified here. And so a couple things. It's a lot less because the mass is a lot greater. So it makes it's logical that the chunk that has a lot more mass is going to have a lot less velocity in order for them to add and sum so that the momentum is conserved. The other thing that jumps out here is the sign. So notice this sign is telling us that it's in the opposite direction. We didn't specify the direction. We just made a cartoon that has one chunk going in one direction. But the fact that this negative sign here is telling us that it's in the opposite direction, which makes sense because when we add them together, it has to sum to 0 because we started with 0. Let me just make a note of that. So even though this is a one-dimensional problem, the sign in that situation does contain direction information. So it's important to have that. Questions on that question? So this is another example. Now, instead of starting with some momentum and seeing what happens, we start with no momentum, and the momentum of the products is going to have to equal that zero momentum. So in qualitatively, I guess something that I would mention is that if you think about it, if you have just to point something out, if you have something break up into pieces, you can't have, if it's at rest, remember this was at rest, you can't have a situation where the products are going in the same direction. Because now if you look at this, this would mean that there's a net momentum in this direction. This is not allowed. Because of momentum conservation. And in fact, this has been used in nuclear physics. You can have a situation where you see stuff that's shooting in one direction, and from that you know that there has to be stuff that's going in the other direction, even if you didn't detect it, because of momentum conservation. Anyway, that's a really kind of interesting consequence of this. So yeah, the velocity was in opposite directions for this question. So we only have a few more minutes. Let me show you one other question, just to give you a little more about impulse. So, and we'll try and be respectful of our time constraint. I'm trying to be better about that. So here's a question for you. You have a golf ball of mass 0.045 kilograms. It's hit off of a tee at a speed of 45 meters per second. The golf club was in contact with the ball for, why is this so small? For 3.5 times 10 to the minus 3 seconds, so 3.5 milliseconds. Find the impulse imparted to the golf ball, and find the average force exerted on the ball by the golf club. So, impulse. This just gives us a chance to recognize impulse. Notice there's a cartoon that's better than the cartoon that I drew for you that gives you the force on the ball as a function of time. Notice it's like a big, it's going to be a spike in force, and then we can relate that to the average force over some defined time interval. So real quick in the last couple minutes, and then we can come back to this too. So impulse is just the change in momentum. So it's going to be the final momentum minus the initial momentum. If it's at rest, the initial momentum is going to be 0. So in other words, this will be the mass of the ball times the velocity of the ball final minus 0. Or how about I'll put it mass of ball times 0. So if we multiply this, we're going to have 0.045 kilograms times our speed, which was 55 meters per second. So this gives us an impulse of 2 kilograms meters per second. And I should draw a cartoon here. We have, it's sitting on a tee, and then it gets, hit by, oh man, I can't draw a golf club, but hit by a golf club, and then it's going to be, moving 45 meters per second. So the impulse that we found for that interaction is 2 kilograms meters per second. And then recall that we can relate this to the average force, because the impulse is also equal to the average force times the time interval. So, and we're given that this time interval was 3.5 milliseconds. So if we know the time, we know the impulse, we can find the average force. is just going to be the impulse divided by the change in time. So 2 kilograms meters per second divided by 3.5 minus 3. This gives us a force average of about 580 newtons. So this is using this idea of impulse. We can relate the force during the impact to the change in momentum. And then the one qualitative thing I would point out is that notice the actual force is larger. So during this impact, the peak force is going to be bigger than the average because the average is just this square as opposed to this peak. So just a qualitative point to make when talking about impulse and collisions. So we'll look at more problems tomorrow. We'll get into, or not tomorrow, on Wednesday, we'll get into conservation of momentum in more than one dimension. But this gives you a start. We can look at another problem with regards to this next time as well. Any questions? So there's questions on impulse and conservation of momentum in one dimension in your homework assignment for this chapter as well. Let me put it to you this way. What questions do you have? Anything so far? Oh yeah, we're going to talk about vectors, definitely. Much of the sort of substance, the real meat and potatoes of this chapter is doing this in more than one dimension. So yeah, let me. Yeah, so that's next time we'll talk about conservation in more than one dimension. That's where you'll get a lot more complicated problems just because you have to keep track of, if you think about it, you have momentum x, momentum, PA x, PA y, PA z, PBX, PBY, PBZ, before and after. You get the flavor, or you can kind of see where that's going to go. So, well, this is just a qualitative point, but notice that by the shape, right? Since the shape has to be smooth. In order for those to have the same area, the peak of this has got to be larger. Yeah, so it's less about vector operations, cross products and dot products and stuff, and more of just keeping track of the components. So it's sort of like doing Newton's laws in 3 dimensions. We're going to find components in x and y, add them together. So it's less about vector math and more about algebra, keeping track of components. Other questions? I'm trying to be more diligent about keeping us from going over. So I am going to sign off here in a moment. Of course, if you have other questions or questions that pop up while you work on the homework, don't hesitate to reach out to me. We'll get them straightened out. We can talk about it in teams, etc. So if there aren't any burning questions, have an excellent day. We will see some of you in lab tomorrow. And yeah, start reading into chapter 9. You can start looking at the homework assignment. And we will see you tomorrow/Wednesday.